In this example, we have a rock sitting at rest on top of a 121-meter high cliff. And the question is, if the rock falls off of the cliff, how fast will it be traveling when it hits the ground? To solve this problem, we're going to have to think in terms of energy. While the rock is sitting at the top of the cliff, it has potential energy. It's sitting still, so it has no kinetic energy, but it does have potential energy. How much potential energy does it have? Well, we have an equation for potential energy. Potential energy is mgh. Well, let's take that equation and fill in what we know. We don't know the potential energy, we don't know the mass, but we do know g. It's 9.8 meters per second squared. And we know the height. It's 121 meters. Notice how I'm abbreviating meters here. I'm calling them MTR. That's because there's an m already in the equation for mass, and I don't want you to get confused between the m for mass and an m in a unit. So I'm going to abbreviate meters as MTR throughout this problem, just so you don't get confused later on. Okay, so we don't have a number for potential energy, but we do have an expression for potential energy. The potential energy as the rock is sitting at the top of the cliff is m times 9.8 meters per second squared times 121 meters. Now, when we're doing these problems, we have to think about the total energy, because that's the one thing that doesn't change throughout the problem. Well, what's the total energy of the rock here at the beginning of the problem? Well, it's sitting on top of the hill. So the total energy is simply the potential energy plus the kinetic energy. We have an expression for potential energy. The potential energy is m times 9.8 meters per second squared times 121 meters. And we know what the kinetic energy is. The kinetic energy is 0 because it's sitting still. So that means the total energy is really just m times 9.8 meters per second squared times 121 meters. Now that's the total energy of the rock, and that stays the same throughout the problem. So at any time, I can use this expression for the total energy of the rock. Well, now let's think about what happens when the rock reaches the bottom. At that point, its height will be 0. If height is 0, then the potential energy is 0. That means its total energy will simply be given by this expression for kinetic energy, 1/2 mv squared. So at the bottom of the cliff, the total energy of the rock is simply 1/2 mv squared. So now we have two expressions for total energy. We have the total energy of the rock at the beginning, m times 9.8 meters per second squared times 121 meters. And we have the total energy of at the end is simply 1/2 mv squared. We can set those two expressions equal to one another. So m times 9.8 meters per second squared times 121 meters equals 1/2 mv squared. Now look what happens. The mass cancels. We have m on the left-hand side of the equation, m on the right-hand side of the equation. That makes the mass cancel. So we didn't need to know the mass to solve this problem. It cancels out in the mathematics. That tells us then that 9.8 meters per second squared times 121 meters equals 1/2 v squared. Now solving the problem becomes a snap. All we have to do is solve for v. We multiply both sides of the equation by 2, then we take the square root of both sides of the equation. That gives us v equals the square root of 2 times 9.8 meters per second squared times 121 meters. When we work out the numbers, we get 49. The units work out to meters per second. So the speed is 49 meters per second.